Let us verify whether this given transformation is considered as a linear transformation. We have here from R2 to R2 given with this transformation equal to this. Notice here we have a transformation of a vector represented by x and y, unlike in previous two videos. So we're going to define as well our components of vectors here properly. To verify whether this is a linear transformation or not, we need to satisfy the two conditions. The first condition is the let's say the transformation of the sum. Let's have certain u vector plus v vector. Okay, the transformation of the sum is equal to the sum of their transformations. Okay, that's what it meant with this. The transformation of the sum is equal to the sum of their transformations. If we could show this one here, then this means we have satisfied one of the two conditions for a linear transformation. The second condition is the transformation of a certain scalar multiple of a vector u, okay, is equal to the product of the scalar times the transformation of the same vector u. So here, let us try to use these two vectors here, u and v. So again, in our previous videos, we were given with x sub 1 and x sub 2 for our first vector x, and we have for our vector y is y sub 1 and y sub 2. Since this our vector is a combination of x and y, let our vector u be the sub 1s, x sub 1 and y sub 1, and our vector v be sub 2s, the x sub 2 and y sub 2. So let's start with the first condition. We have here the transformation of the sum of the two vectors must become the sum of the transformation of the two vectors. So with this, let's try to substitute the components of each vector, x sub 1, y sub 1 plus x sub 2 and y sub 2. Before we could apply the transformation, let's add the two vectors. You have x sub 1 plus x sub 2, y sub 1 plus y sub 2. Once we are done with this, let's now try to use the transformation as defined with this. So you have your first component, that would mean the entire of this. So you have x sub 1 plus x sub 2 minus twice the second, y sub 1 plus y sub 2. Then you will have twice the second, y sub 1 plus y sub 2 minus the first. Let's use parentheses to denote this one, especially if it's preceded by a minus sign. So from here, let's try to multiply. Let me use some spaces here. X sub 1 plus x sub 2 minus 2y sub 1 minus 2y sub 2 as we distribute that. The other side, 2y sub 1 plus 2y sub 2, distribute that as well, minus x sub 1 minus x sub 2. Here, since our goal is to come up with a transformation of u and transformation of v, where u contains the sub 1s and v of course sub 2s, let's try to manipulate this entire expression here, both of them, where we are going to combine the sub 1s or pair the sub 1s and the sub 2s. That would mean x sub 1, I will start with 2y sub 1, so they would be sub 1s here. Then the sub 2s, x sub 2 and minus 2y sub 2. The other side as well, 2y sub 1 minus x sub 1 plus, that's plus, 2y sub 2 minus x sub 2. After arranging them, let's take out the sum of the two vectors using the components of sub 1s and sub 2s. So you have x sub 1 minus 2y sub 1, comma, this here, 2y sub 1 minus x sub 1, plus you have here x sub 2 minus 2y sub 2 and 2y sub 2 minus x sub 2. Notice that we have here all entries with sub 1s, and it actually fits the definition here, x, okay, 2y, here 2y, and then minus x as well. This, and as a second, you have sub 2's x here, 2y, 2y, and minus x. This would mean the first vector here is just the transformation of your vector u, okay, as u contains your x sub 1s. And for v, which contains your x sub 2s, you have the transformation of your v. This has satisfied the first condition. Okay, so our first condition has already been satisfied. We have shown that the transformation of the sum is equal to the sum of the transformation. Next here is to satisfy this, where C is any scalar. And if we're going to have T times C, scalar of C scalar times U, we're going to substitute here C times your component of U sub 1s, x sub 1, x sub 2, which is actually the same as you have C x sub 1 and C y sub 1. We need to come up with this form where C is already outside the transformation, and if we could do that, then again we have satisfied condition 2. So let's now apply the transformation here. Your first entry minus twice your second entry, Cx sub 1 minus twice your second entry, then twice your second entry, y sub 1, okay, and then minus your first entry. Since our goal is to come up with the C outside the transformation, let's see if we could factor C here. So factoring C, x sub 1 minus 2y sub 1. Factoring C, 2y sub 1 minus x sub 1. Since C are both present in the combination, okay, combinations of, composition, okay, of our two entries of this vector, we can take it out. You have x sub 1 minus 2y sub 1 and 2y sub 1 minus x sub 1. And as you can see, this here is actually the same as the x minus 2y, 2y minus x. This means that we have shown that this is C times the transformation of your vector u. Now we have also satisfied the second condition together with the first condition. This would mean that this given transformation is really a linear transformation. So you just need to really check whether these two conditions have been met using this process and use algebraic operations in solving for such. And if again one of which will not be satisfied, then this is not a linear transformation, but in this case we have satisfied both, so we have here a linear transformation. Thank you very much for watching.